Hello, everybody. Nick Gubbins from Colorado State University back again. This time to dig in a little deeper on chemical weathering and talk about some of those concepts. So the learning objectives for this video are, by the end of this video, students will be able to describe the different types of chemical weathering reactions, um, understand better the effects of pH and temperature on chemical weathering, and understand biology's influence on chemical weathering. So let's jump right into those reactions. So chemical weathering takes place, that's a pretty broad umbrella term, through a whole bunch of different reactions, and we're going to hit on just a few of the more elementary ones of them here. And in the real world, these minerals are weathered by usually these complex chains of them. But a lot of the ones that I'll show you are going to be simplified or just single steps of them. But know that out there where things are complicated in the environment, it's usually cascading chains of different mixtures of these kinds of chemical weathering reactions. So let's talk one of the simplest ones, which is hydrolysis. And hydrolysis is just when water reacts with a mineral to loosen the bonds in that mineral structure. So if you remember, water is H2O, but it also exists as hydroxide and hydrogen ions in solution in small amounts. And so in hydrolysis, one of those hydrogen ions can attack and replace one of the cations in a mineral. So an example here, off to the left, is of potassium feldspar, and when it interacts with water, one of those hydroxides and the potassium can be split off, and that gives you quartz and then a clay, and then some ions in solution. This is often aided in reality by CO2 dissolution, creating a slightly acidic mixture, increasing the amount of hydrogen ions in solution. That's called carbonation. I'll talk about that in just a minute. But simple hydrolysis is the starting point for many weathering sequences, and it's all over the place and affects a lot of minerals, except for things with a nearly perfect crystal structure like quartz. So let's talk about carbonation then. So carbonation is just when CO2 will dissolve into water and create carbonic acid. So we've seen this a whole bunch of different times in the carbonate lectures, in the acid-base lectures, ocean acidification, all sorts of stuff. So CO2 dissolves into water. Like I said, it's super common. An example of this is rain falling through the atmosphere. The atmosphere is like 400 parts per million CO2, so rainwater pH is usually a little acidic, like around 5.6. And this lower solubility this lower pH increases the solubility of some minerals. So calcite off to the left is one of those. And that's just because of solubility effects. So if you go back to my solubility lecture, we talk about how the free hydrogen ions in solution can react with some of those products and then make room in equilibrium for more dissolution of calcite. So this is especially important when we're thinking thermodynamically at lower temperatures. So temperature, as I'll talk about more in this lecture, is a master control on weathering rates. And when there's very low temperatures, things would proceed very slowly. But if you remember from our gas lectures, lower temperature water actually can dissolve more gas into it. And so in underground caverns and groundwater especially, where the temperature is down closer to like 50 degrees Fahrenheit, a lot more CO2 can dissolve than up at warmer surface waters, and then this carbonation effect can be very important to driving weathering reactions. Like I said before, carbonation and hydrolysis often are just sort of in the mix together. So if we go back to that feldspar example that I gave you in my hydrolysis slide, this is that same reaction with carbonation. So if we look in blue is the potassium feldspar, and then if you add CO2 and liquid water to that, you're going to get a potassium ion, bicarbonate ions, then this acid, this salicylic acid, and then this red here is chlorite clay. And you can see that this is just a slightly more weathered version of the hydrolysis reaction that you saw a couple slides previous. So the key concept here is that hydrolysis is when water weakens a mineral's structure, and carbonation is the reaction of minerals with water acidified by carbonic acid. All right, a little less elementary is oxidation. This is a common weathering reaction when minerals first become exposed to the atmosphere. And oxidation, put very simply, is just the transfer of electrons. And there's two different sort of halves to an oxidation reaction. We talk about one thing being oxidized and one thing being reduced. So in oxidation, something loses electrons, and in reduction, it gains electrons. This is a process that is very, very slow when it's not in the presence of water, but it's pretty quick when it is hydrated. So I'm not going to get too into the weeds on oxidation and reduction, but I'm going to show you a little conceptual diagram here on the next slide to hopefully make it more intuitive, and then I'll give you an example. So in an oxidation reaction, you essentially have something going from a higher oxidation state to a lower oxidation state. So we say that the reducing agent is oxidized, and so in that case, compound A is going to lose electrons, and we say that the oxidizing agent is reduced. So that's the thing that loses electrons. And so in environmental chemistry, a good bet that you can make is that wherever there's oxygen present, it is the oxidizing agent. And that's just because it is very electronegative. It's one of the most efficient oxidizing agents. And so basically wherever it is, that's the thing that's the oxidizing agent. So an example of that is pyrite oxidation. So pyrite is fool's gold on the bottom left there. It's FeS2, and in the presence of water and in oxygen, so in surface waters, for example, because our atmosphere is like 20% oxygen, it will react to create a ferric oxide and then sulfuric acid. So in this case, we would say here the reducing agent is going to be pyrite. Ferric oxide is what it is being oxidized into. Our oxidizing agent is oxygen here, and then that is being reduced into sulfuric acid. This is a very important weathering reaction because, as you can see here, acid is one of the products of this reaction, and then that can go on to increase the weathering of carbonates. So here is a figure from one of Matt Ross's papers. And it's a conceptual diagram here showing just exactly what I had just gone through. So you've got pyrite is that little golden nugget, that fool's golden nugget up on the top left. That is oxidized in the presence of oxygen and water. That gives off the sulfuric acid, which supplies hydrogen ions in solution. And then that, in turn, leads to enhanced weathering of those calcite minerals. And then because we're already under very acidic equilibrium conditions, that CO2, instead of staying in the solution as bicarbonate, is going to off-gas as CO2 gas. And so where there is pyrite oxidation, not only do you get faster carbonate weathering, but you also have this weathering acting as a geologic source of CO2 in the atmosphere. So the key concept here is just that oxidation reactions drive weathering when minerals are first exposed to oxygen. And we'll get more into the nitty-gritty on reduction and oxidation in subsequent lectures. All right, so that's some weathering reactions. Now let's talk about different types of chemical weathering. So a lot of times we like to talk about weathering based on the products that it creates. And we've got two main classes of that. So congruent weathering just occurs whenever a mineral is completely dissolved. So a solid goes in and you get aqueous ions out. Incongruent weathering leaves some kind of solid behind. So a solid goes in and then you get some ions in the water, some aqueous solutes, but then also there's a solid left over. So everybody's favorite example to use for everything, including congruent weathering, is calcite. So here we have calcium carbonate, aka calcite. You add it into water, you get a calcium ion, you get bicarbonate ions, and there's no solid left. An example of incongruent weathering would be this slide that I've already shown you. So feldspar going into clay, or weathering down into clay. You can see we added water to this feldspar, and we got a clay solid, and then a bunch of ions, including that silic acid in solution. So incongruent weathering is the basis of soil formation. And every time that there's incongruent weathering, if I can bring back up this handy figure here, every time there's incongruent weathering, what you're left with is less weatherable than your initial mineral. So you just keep going through degrees of substitution for each imperfection in the crystalline structure of that mineral. And so, for example, if we start with a potassium feldspar that is right above muscovite mica, so it's on the right 3 up the chain, that can then be weathered down further and further, and as you saw in our previous slide, here we were getting eventually this was going to weather down into a quartz, so 4 silica, 8 oxygen. And like I said, this differential weathering and leaving products behind, this is the basis of soil formation. And we're going to talk about that more in future lectures. So the key concept here is that all products of congruent weathering are fully dissolved, and incongruent weathering leaves behind a less weatherable solid and then some dissolved products. So let's talk about some of the, let's get more into some of the controls on weathering. So the big one for that is temperature. So if you remember back to our thermodynamics lectures, all chemical reactions are, the rate of them is determined by temperature, because temperature describes the movement of those molecules, and those molecules need to be moving around to smash into each other and react, and weathering is no different. And that is described in the Arrhenius equation, which just says that as temperature increases, so too will reaction rate. So for my previous lecture, this amazing figure from Hartmann et al. In 2014, they calculated chemical weathering rates across the world, and you can see here this figure also takes into account the water availability, which we've talked about is very important for many chemical weathering processes. So very dry places like Australia and deserts like in southwestern United States here, they have very low weathering rates. But if you look just below the equator, where temperatures are high and there is water, that's where we've got our highest weathering rates. And so put very simply, temperature controls the rate at which weathering reactions occur, and higher temperatures are going to yield faster rates. Another control that we've talked a bit about is pH. And like I said, there's a ton of different sources in the environment for pH. So like rainwater, again, is slightly acidic. But those weathering reactions that we've seen are a way to take some of those hydrogen ions in solution and neutralize them. And so they get turned into other products and bind with other solutes. So pH has a big effect on solubility, and then solubility determines how quickly those things can be dissolved. So we talk about this relationship between pH and then solubility, and sort of what form these solutes will take in something called predominance diagrams. So in my previous lecture, we talked about aluminum hydroxide ion complexation and how it changes with pH. So here is the predominance diagram of that same mineral. This is a little different than the speciation diagram that you saw, because that was just what form is it in by pH. This here, if you look on the x-axis, it's still the pH, but then on the y-axis now we have what is the concentration of aluminum in solution. So regardless of pH, here you can see that aluminum hydroxide with no charge is the most stable form if you have a ton of aluminum in your solution. So if you go high enough on the y-axis here, aluminum hydroxide is going to be your predominant species. However, under normal sort of pHs, environmental pHs, so circumneutral, with enough aluminum, you're going to end up with this Al3+, aluminum 3+, and that is super, super toxic. And if you remember back to the solubility lecture, here's that slide again from it. In basic conditions, we have this pH effect that's going to favor creating AlOH4, so this more complex version of it. And so as you move to the right here, on your pH scale, so on the x-axis, you can see that after a pH of about 7 and into 8, it starts favoring having that ion complex form. So a practical example of this, these are super useful, these predominance diagrams, but a practical example of this is chromium pollution. So chromium is something that is not great for people to be drinking. And so water managers will often use predominance diagrams to plan how they want to get chromium and other pollutants out of wastewater. So electrodialysis is the process through which you can pump water across membranes, so selectively permeable barriers, and then have the electrodialysis just comes from having charged anodes and cathodes on the other sides of those membranes to pull certain solutes through it. And so what Water Manager will do is they'll use these predominance diagrams to try and leverage the differences in size and solubility and charge of the solutes and the forms that they're in to remove them from wastewater. So here is the predominance diagram for chromium. And you can see in raw wastewater, which is pretty acidic, you can see there's a chromate here that is pretty soluble and very toxic. And we would prefer to have out of our water. And so if to the left here, this chromic acid, H2CrO4, that's highly soluble. And divalent chromate, CrO4 2- off onto the right there, so in very basic conditions, that is not all that soluble. And so a common way that water managers will try and get that out in an electrodialysis system is first they'll increase the pH, so they'll make it very soluble, and they'll go ahead and concentrate it. So they'll run it through a bunch of electrodialysis filters, and they'll get a high concentration of chromate into one amount of one pipeline of their effluent. And then they can reduce the pH and add in some cations. And by doing that, they can precipitate out the divalent chromate as calcium chromate or sodium chromate or something like that, and then strip it out with an opposite permeable membrane. So the key concept here is pH affects both the weathering rate and its end product for now. I say for now because the big green machine keeps on rolling and all of that is going to turn into some other product. And generally, very high or very low pH increases rates and the extent of weathering. So life and biology have an impact on weathering rates. And that's just because things in the living world are interacting and they are increasing entropy. And they can do that mechanically and chemically. And they do that for a bunch of reasons, and basically all of them are self-interested and have nothing to do with controlling weathering rates. They're just for their own gain. So common one here, shelter. So there's cute little prairie dogs. They're going to burrow. That's going to mechanically weather soil. It's going to let water get further down into the soil profile and change the weathering there. They'll do it for nutrients, either for digging for food or, for example, tree roots will chelate. That is just add acid and add compounds to loosen up rock to free up needed minerals. And we're going to go into that in just a bit. They'll do it for energy. So the bottom left there, you should recognize the bright orange color of oxidized iron. Bacteria can oxidize iron for food or for toxicity management. But the big point here, and one that I'm going to impress on you, is that all of these reactions are important. They all contribute, but the big one is trees. So they're all over the place. They're the most dominant. Angiosperms are the most dominant sort of plant life on the planet, and trees are a big part of that group of plants. And they are very efficient mechanical weatherers. They exist all over the place, in rainforests and alpine areas, temperate forests, all over the world. And then they're also chemical weatherers, which we'll talk about in just a bit. But the rest of these are, I don't want to say a rounding error, but they're quite small compared to the effect of tree roots for biological weathering. So let's talk about one of those smaller examples first. So I had noted that you should recognize that orange from the oxidation of iron. And certain bacteria can indeed oxidize iron out of solution in order to create biomass. So this is called photooxidation here because it takes a little bit of energy from the sun to make this thermodynamically favorable for the bacteria. But if you've got bicarbonate in solution, so that could just be from water being exposed to CO2, so that's carbonation there, and then some sort of, you've got unreduced iron, or unoxidized iron, excuse me, and sunlight, that can react to form formaldehyde, which is, for bacteria, can be the starting point for biomass, and then we've got an oxidized iron here, an iron hydroxide, and then some acid. So in this case, we'd say that iron here is the reducing agent, and it is getting oxidized iron. And then bicarbonate here is our oxidizing agent, and that is getting reduced into precious biomass. Because if you can imagine in a little pond on the slope of a volcano, there's not a ton of biomass that's just falling into there all the time to make it easy for bacteria. Okay, a much more prevalent example is going to be tree roots and the carbonic acid pump. So I'd mentioned before that roots aren't just mechanical weatherers, which is probably the one you think of, like seeing a root snake its way into a crack in a boulder and make it even bigger, like is in this picture here. But they also chemically weather, and they do this by respiring into pore water in the soil. So you probably think of plants as photosynthesizers first and foremost, and they are, but parts of them photosynthesize and parts of them respire. Well, I guess all of them are respiring because it's living, but the balance. And so roots are one of those parts that are respiring all the time. And so the blue reaction underneath that picture there, that is the respiration reaction. So we have glucose, that's that big hydrocarbon, plus oxygen gives you water, CO2, and then the energy that you need to keep on living. And if you recognize the reaction just below it, that can create a carbonation reaction. So if you've got your tree roots in soil water, so there's soil packed around them, and then in those soil pores there's water, they're then off-gassing their CO2 into the water, and then that is right there, carbonation. And so, like I went through with other carbonation reactions, the carbonic acid is going to lower the soil pH, and then that lower soil pH can weather phosphorus-containing rocks and give up more phosphorus for the tree to grow more quickly. So let's get into that. So here is just that carbonic acid, so that's what's being formed from CO2 dissolving into water. And that's giving us a hydrogen ion and then bicarbonate in solution. So an apatite rock, like Ca5PO43OH, can then interact with that increased acidity when it's in water, and sort of the opposite of what we'd seen in aluminum hydroxide, we can then pop off that hydroxide now under acidic conditions, and instead a water is going to take its place electrochemically, and that could then dissolve even further. And in the presence of more hydrogen ions, so when the pH is low enough, that calcium phosphate now can react even further. And then if we have even more acidity, we can sort of keep doing the reverse complexation here, and we can get it all the way to having just a phosphate here. And so if you remember initially, this apatite rock here, this phosphorus-containing rock, phosphate-containing rock, the plants can't use. But now that it's been weathered through a carbonation reaction, plants can use this phosphate. And so the sort of central takeaway here is that by lowering the pH in the soil, these tree roots then increase the amount of inorganic phosphorus in the soil. And so trees are essentially being rewarded for weathering out this rock faster than their neighbor. Because if you remember, phosphorus is a limiting factor or limiting nutrient for plant growth a lot of times. And so the faster that they're respiring and the faster they're growing, the more that they can strip out this phosphorus from the rock. Because if they don't do it, their neighbor will. And then that allows their tree root to keep chugging through the rock, keep growing, and keep accessing more nutrients for the tree. And a cool feature of this is that under very acidic conditions, this H2PO4, this phosphate here, will actually complex with metal ions in the soil, so things like aluminum or iron or whatnot. And that is, again, unavailable to plants to use for their growth. And so if a plant is growing sort of runaway growth and is respiring a ton of CO2 into the poor water, and it brings the acidity down too low, that actually slows down the root growth of the plant because it's locking that phosphorus back up, and it works sort of as a self-stabilizing feedback loop, limiting plant growth, reducing respiration, and then giving it time for that to drain out or be replaced with those soil pore water, and then have the pH head back towards circumneutral. So it's this really interesting and elegant interplay between weathering and life. So key concept out of all this is biology generally favors higher weathering rates to access energy or key nutrients. So cool. Here's my works cited and my many, many media credits, but thank you so much. And in future lectures, we're going to be tackling soil formation.